Alright, welcome back. MECH2320. We're skipping ahead to chapter 23. The reason we're skipping so many chapters is because we've already done that multiple times. We've covered that stuff in the electrical class. We're covering it in the PLC class. We've covered it in fluid power. We've covered it in the mechanical class. So you guys should have a good grasp of what's really going on between chapters 13 and 22 from now on. So don't worry that we're skipping that much. You can look back through it, but it's really just going through different components and sensors and things like that we've already done multiple times. So I think you guys are pretty comfortable with that. I mean, we started that stuff back in digital electronics back your sophomore year for some of you guys. Other you guys never took that class, so I understand that. Okay, but we're going to go through chapter 23 here. We're going to do across the line starting. Okay, across the line starting. It's the most common starting method that there is. And when you are starting across the line, okay, it's accomplished because you're directly connecting the motor to the power line. Okay, very, very common. And we use it with AC and small DC motors as well. Okay, so very, very important for that that we can use it. In the motor size, okay, it's going to vary just depending on what the service that we need done. So it's not going to be this only works for this horsepower or this horse. Okay, so it just depends on what the service is, but we can cross the line starting directly connect it up. All right. Obviously, most common motor, right? Squirrel cage motor, induction motor type, scenario. So we have wound rotor and synchronous motor. We covered a lot of that in the mechanical class and the electrical class. Kind of how the motors work. So I'm not going to get into like the nuts and bolts of looking at understanding how the signal's going through the rotor and the field and that sort of thing. But why do we use those? All right, the most common one was the induction motor, right? It can produce much more horsepower. All right, we don't need separate set of start windings, commutators, or brushes with those. Okay, remember we're talking AC here. There's no DC stuff on this piece, but all right, and they're very efficient and they have a long lifespan. All right, they tend to last, just hours and hours and hours of service. Okay, so just remember, this is the stator, okay, on your motor. So remember, when we're doing AC, we are changing the field in the stator. Okay, remember currents going in here. If this is a three-phase winding, right, we have three different phases going into the windings, and we're changing the magnetic field in the stator. So we're rotating the electrical field here in the stator, and that's inducing the rotor, okay, the rotating mechanism on the inside piece to turn. Okay, so just going through, right, and when we do three-phase, okay, it's based on how the stator core is winding or is wound. And I'm going to step back a slide so you can see how the different windings look. Okay, and in the direction of the wire it matters because remember, back from electrical, left-hand rule, thumb in the direction of current, fingers wrap around and give you the direction of the magnetic field. So that's, we got to be able to change that back and forth. Okay, that works well with AC as well. Also, when it's three-phase, okay, phase 1, phase 2, and phase 3, they're all 120 degrees out of phase with each other. We covered that in the electrical class as well. And understanding that when we also talked about leading and lagging current, or leading and lagging voltage, in that aspect when we talked about sinusoidal waves and things like that. And the biggest fact that really helps here with AC, right, is that the polarity changes. Remember, AC is going up and down. It's a sine wave, right? So we have a positive amplitude and negative amplitude, a positive amplitude and negative amplitude. And that's really just changing directions. Remember, it's not really a negative number. It's the directional change as it alternates between positive and negative. Okay? Now, we can also do laminations, okay, where we're protecting the coating on the winding there. It's really just, a coating on the winding. Think of like a coating on the like your cords or your electrical wires that you buy at the store. It's the same kind of thing, but it's not a heavy-duty coating. It's to help prevent arcing and those sort of things. And it really makes it look kind of like a solid piece of metal. And I've shown you guys the motor in class, so you kind of see what it looks like when it's laminate coating. So, here's the picture up the upper left-hand side. That's without laminate coating on. That's what, and that's why it's called squirrel cage, even though it looks more like, right, a hamster cage where you sit there and spin around. But on the upper right-hand side, that's just like the one we have in class, okay, where you can actually see, what it looks like with the laminate coating on. So it looks like that copper kind of piece in the middle. All right, but essentially that's what it's looking like. So on the bottom right hand side, you can see what the squirrel cage looks like without the windings on it. So we put all the windings on, and then we put that laminate coating on it, just so you can kind of see. And this is just the rotor, all right, when it's cut in half, so you can kind of see what everything looks like. 'Cause it's great to see this stuff when you actually get a view of what's going on. And just remember from the mechanical class and things like that, how the field's changing. So notice the little gray piece around the outside, okay, that's our changing field, all right, and we're inducing it on the stator piece of the motor, okay. So our stator moves around on our rotor, okay, so the stator is changing fields as we give it electricity, right, and it's inducing it on the rotor, okay, or the armature, however you want to do that, in forcing it to rotate around. And remember, everything is set up so that it is what? Opposites attract, likes repel. So we got to use opposite polarity so that it induces it and pushes it around. Okay? All right, so let's figure out, how do we figure out the speed of a motor, right? We can use a tachometer. You guys did that in mechanical class. And, we want to know what's the RPM on the motor. Is it 1200, 1700, different things like that. So we can go through an example here and do some just a basic calculation. And like I said before, this class, we're not really heavy on mathematical computations. For me, the focus, you read schematics, you're able to wire things up, get motors to run, push buttons to work, understanding timers, relays, all those different things. And it's really heavy on the labs in this semester, okay? But let's do an example here. We want to find the synchronous speed of a three-phase motor that contains 3 poles per phase, okay? And it's connected at 60 hertz. Well, the number of poles does matter, okay? So it's very important that we understand how to do this calculation. So the equation for this, S, that's our synchronous speed, okay, 120, okay? And then we have F, which is our frequency, all right? And P is the number of poles that we have to do this calculation, okay? So when we substitute in our given values, we're going to take 120 times 60 divided by 3, all right? And we're going to get 2400 RPM. I mean, essentially, that's how we calculate the RPM of a motor, okay? So when you put the tachometer on this motor, we should be doing that, or getting 2400 RPMs. Okay, now DC, all right, you guys saw me do this in mechanical class. We had the little example motor, right? We've also passed it around. Remember, a DC motor, okay, we're not using induction here, okay? We're not using induction because the DC motor, the stator has a permanent magnet on it, so you see that it's north and south. It's locked in, so the stator has a north and a south. It's as we have the windings on the rotor, and you can see the rotator rotating in my example here. Now remember, we have brushes here, so the brushes, okay, connect the commutator. So we send the current in through there, and we can change the direction of the current using the brushes. So when this happens, okay, the current in the windings changes, all right, and as those repel and flip, all right, we're going to make it the way it's wound, all right, so that it appears that when we have north on south and south on north as it rotates around. So it pushes it that way. It's constantly changing polarity, and that's what causes it to change. What's changing on the polarity is the rotor, not the stator. The stator, it's fixed. It's north, it's south, and it's a permanent magnet. Okay, so this is the difference. We've covered this before, so DC motors we should understand. Okay. And sometimes we have DC motors, we got a pickup coil and holding. All right, so this is just for texture here. So remember, we've already talked about the blowout coil as well. So we can use a limit switch that opens up when the armature is actually attracted to the magnet. Okay, so we have something that helps us get through that. Alright, so we did cover this in chapter 5, but just know that we use this, to suppress, or it's as arc suppression, okay? And we got into a little bit of detail, but alright, so it remains, there's 2 coils on it, so one is a holding coil, and that one's going to remain energized, alright, as long as we have power that's applied to the contactor. And then the pickup coil, right, we're going to use that to increase the magnetic field strength, alright, as soon as that contactor is first energized. Okay, so we're just there for arc suppression. We have a lot of those kind of issues, and that's why we have interpole windings and things like that to help arc on the other ones as well. Okay, but this one's for DC. Okay, so when we have direct current motors, okay, we only have one load contact or one overload sensor on it. So on the left hand side, that's what's highlighted in blue here. Alright, we have a contactor and we have a thermocouple. Alright, because we are only going to have one possible load when we have DC. So this should make sense, right? You're only going to have one line in to power it, just with direct current. There is no such thing as 3-phase DC or anything along those lines. Okay, so just note that we will always have it protected that way. Okay, now if we want to have multiple contacts, okay, we provide a higher voltage rating on this. Okay, so that's really just the whole reason. If you do get a DC motor that has multiple contacts on that, it will increase, all right, and give us a higher voltage rating for it. So, guys, that's really it for across the line starting. We're directly wiring right up to the motor, and things are good to go as soon as we hit the start button. So whether we're doing AC, whether we're doing DC, and we've done a little bit of motor review as well. Alright, as usual, email me if you got any questions. Let me know if you need a team meet or Zoom meet or anything like that. Else, guys, have a great day. See you in class.